scientists argue about where life began. I think life began in the deep sea vents. I think life began in hot springs on land. And I think life began in an impact crater. Okay, people, life began in the vents. And how do we know this? Well, first off, look at this vent. What a beautiful thing, okay? Nice little vent. And you can see here that if you are trying to get membranes, we can think about membranes, look at them, they exist. And so that provides an easy kind of existing cell to start to do experiments in. And you can imagine thousands or millions of these little mineral cells life gets to. It's kind of an experimentation zone for life to run in. And here on the right, you can see an autotrophic cell, just a normal cell, has the cytoplasm on the inside, it's alkaline in the middle, and then on the outside it's acidic, and you use electricity to push hydrogen outside the membrane and then pull it back through with ATP synthase. And so that is very similar. You can see proton gradient across an organic membrane, which is pretty similar to a proton gradient across a thin inorganic barrier, where you can imagine a bunch of H+, this H2, primarily from serpentinization, this process that produces lots and lots of hydrogen into the water. And this only happens in these very alkaline vents, where the vent is very alkaline. You can see that alkaline hydrothermal fluid, the OH-. And so inside there's OH-, while outside there's a bunch of H+. And that looks very similar to the cells today. These vents also have iron. And so what you can get is you have CO2 and then you have electrons, and you can put the electrons onto the CO2, starting to create these longer carbon chains. And so the fact that there's also iron in these chimney walls acts as a little wire, like a little electron wire, to help create some of those initial reactions for life. And the other thing is that the tree of life, the creatures that you could make in these deep sea vents, look very similar to the creatures at the start of the tree of life. So if you see here's Aquifex, here's Thermatoga. Those are, a Thermatoga is like an extremophile that exists in a very thermal, hot environment, like the creatures in these alkaline vents in the deep sea at the start of life. And so yeah, I think that all of you surface chauvinists think that only life can exist above the surface. It's not. It's down under the subsurface, it's in the deep sea, and that these little mineral cells with all of this H2 around, all of the amazing H2 reducing capacity, plus the iron around the membrane and the CO2 in the water to start to build up lots of carbon molecules down there, and then to output it through these little membranes. And then you eventually start to get the proto-molecules of life and the proto-cells and the long polymer chains needed for the rest of life. Okay, I think that life started in the hot springs. Hot springs are great, and let's look at why early life may have started in the hot springs. So imagine this. This is the beginning of life. You had these little hot springs that were all these little pools that you could start to create life, and then they started there and then eventually moved into the oceans. One of the crucial issues with early life is what's called the water paradox. In order to create these long peptide chains, or just long chains for RNA and also the long chains for proteins, you need to do a condensation reaction where you actually dry it out. You remove an H2O, essentially do evaporation, and that creates these longer chains. While vice versa, if you have a bunch of chains existing and they get too much water in there, they start to break apart. And so it seems crazy to me that you think life would actually begin in the ocean where there's way too much water. It's very hard to create long chains when there's too much water around because it breaks up those chains. And so instead what you have is a situation like this, wet-dry cycling, where you get wet, you are able to, that breaks up all of the little vesicles, all the little molecules. Those then you start to evaporate, that turns into a gel phase, these longer chains, and then you fully get a dehydration where then you have a certain set of molecules that survive that process. And so through wet-dry cycling, you have this part one, dehydration synthesis of polymers between these lipid lamellae. And then after that, you have the encapsulation of polymers within protocells. And then you have the testing of protocells for stability. And then you have the delivery of surviving protocells to the surface area of pool during the dry down. And then 5 is you have the protocells interact within gel aggregate, the progenote, which is this initial set of cells that are all kind of interacting with each other. And then those protocells dry, fuse, and couple polymers back into lamellae. So you're getting a creation of protocells and also creation of polymers through this wet and dry cycling. And as that's happening, you're getting these polymers that do little roles. Some of them are providing stability for the system. Some of them create pores so that you can bring stuff in and out. Some of them create metabolism. Some of them start to have replication or catalyze their own replication. And so over time, you get increasing functions of those polymers. And in the end, you get, this progenote where you have a network of all of these little membranous cells, protocells, all creating these long form polymers within them that provide stability, that provide replication, that provide pores, and they start to interact with each other and share them with each other. And this is really the library and the experimentation of life. It's like life was starting to create a own niche. It's essentially doing niche construction where it's creating its own niche of all of these different polymers that it can start to create through wet dry cycling, then finds polymers that provide good roles, shares them with other cells, and before long you get things that look like protocells and eventually things that look like cells. And so what you have here overall is a PIM system, PIM, probability shaper, interaction network, and memory system, where you have something that's shaping the probabilities of the system. You have an environment that is saying, oh, let's create more stability, let's create more pores. And then those things are interacting with each other because there are lots of these little protocells. So you have an interaction network. And then finally you have a memory system where each run through the wet dry cycling, you can remember what worked well last time. What are the polymers that produce stability? What are the polymers that produce pores and replication and so on? And so you have this beautiful system, probability, interaction, and memory, looping, looping, looping. So yeah, that's how you created life at the beginning. It was in the hot springs because you want it to be wet and dry. You can't have it to be too wet, but you can't have it just be purely dry. And through that wet dry cycling, you get lots and lots of protocells that are interacting in a network with each other to create the beginnings of life and the protocells of life. Hey guys, I'm James Tour. I want to talk with you all. James, shut up, dude. The scientists are talking. Yeah, James, sorry, man, but the real scientists are doing real science here, so just take a break, please. Hey y'all, what's up? I don't think that life was created in the vents or the hot springs. I think it was created after an impact crater. And here's why. So I'm like a John Sutherland type, and I think that you need to have systems chemistry to create all the building blocks of life. And so in order to do that, you need to create membranes, while you also need to create metabolism, and you also need to have catalysis, and you also need to have a genome to remember what's happening. In order to create all of this, you need lots of nitrogen and also lots of carbon. And so nitrogen usually exists in this highly reduced form down here, NH2, where it gets put onto a bunch of the molecules at the start of life. And then carbon exists in mostly in the middle here. It's not as methane, but it's not as CO2 generally. It usually exists in this middle form, kind of like sugars or formaldehyde. But the special thing here that I really want to talk about is HCN, hydrogen cyanide. And HCN is a very special molecule because it has carbon, but it also has nitrogen in it. With hydrogen, carbon, and nitrogen, you're able to actually produce the rest of the molecules needed for life. And so you can see here in this kind of complicated image that if you just have something like HCN up here, hydrogen cyanide, from that you can create all of the amino acids and all of the early carbon chains and all the things you might need for life because it has both carbon and nitrogen in it. The issue, of course, is where does that form? In HCN, or hydrogen cyanide, it is able to produce these longer carbon chains, especially with something like hydrogen sulfide, H2S, where the sulfur brings in the hydrogen and the hydrogen is used, donates electrons in order to turn the HCN into longer carbon chains. And so this might happen in something like one of these impact craters. You have that provides some of the energy to produce something like HCN. HCN is not a natural thing that occurs, but can occur in these plasma-like environments where you really are able to create it in an intense way. And then in these situations as well, through volcanic outgassing and other things, you get hydrogen sulfide or other forms of sulfur that are able to help these interactions occur. And so the crazy thing about this, obviously, is that the start of life on Earth, it looked like this. The moon doesn't have plate tectonics, and so we can see all of those craters from impacts from space. Earth doesn't look like this, but at the beginning of the Earth, we did have tons and tons of asteroid hitting the Earth through the late heavy bombardment, where we had massive asteroids hitting the Earth all the time, creating in impact craters, providing the hydrogen cyanide and some of the sulfur necessary to get these interactions started at the beginning of life. And so yeah, I think that Life likely started in an impact crater because it provides you the hydrogen cyanide, the carbon, and the nitrogen needed to build the building blocks of the rest of life. So I hope this helps you understand a little bit about where people think my life may have began. I don't know where I fall on this. I am very tempted by very convinced in some ways by the water paradox, where it's like, oh man, it's hard to produce life in water. Wet dry cycling is very tempting. Things where there's less water, where there's some water but less water around, are very tempting. And I don't know, I hope by the end of this century that we will have been able to reproduce life. Right now we're just hypothesizing, kind of shooting the shit, seeing if we can understand what is going to happen. Thank you as always for watching, and thank you to Roots donors for supporting this channel. If you want to understand more about the past and how we got here, check out the previous videos here. And if you want to understand the future and where we're going, feel free to subscribe here. Hope to see you then. Bye.